Hello, my name is Susanne Schnell from the University of Greifswald in Germany, and I'm giving today the educational talk on 4D-flow MRI. Why are we interested in measuring the blood flow in the human body? Well, first of all, we would like to visualize the blood flow, ideally in 3D and time resolved. This would allow us to see certain issues in the vascular system visually and also assess this in a rather qualitative manner. The other thing we are interested in is to understand the influence of the hemodynamics on pathologies. For example, why are aneurysms forming, or why are plaques forming, and why at certain location? Why are aneurysms or plaques rupturing? Or how fast does the blood flow through a diseased valve, and so on and so on. So there are many questions we would like to have answers for, where potentially measuring hemodynamics can help. How does the velocity encoding work now? An MRI signal is a vector with a signal magnitude and a signal phase. Usually the signal phase gets discarded because it doesn't carry important information. However, the phase can also be used to store information because it is proportional to flow. So we could potentially measure the blood flow or the tissue motion by using the phase information. This is done by using a bipolar gradient, and together with the local velocity, this is proportional to the phase. Here is an example. If we have spins that are not moving, so-called static spins, then after switching a bipolar gradient like this, the phase accumulates to a certain amount and then goes back to zero. If we have moving spins, for example in blood or tissue that is moving, then we have at the end of this bipolar gradient a phase accumulation that is proportional to the velocity the spins were moving. There is an unknown background phase, however, and in order to get rid of this, we are typically acquiring first a reference measurement, then a measurement in one flow direction, and subtract these from each other. This is how this is done. First, we acquire a flow compensated scan, sometimes not. This is done in a different manner, but here I'm showing an example with flow compensation. That means that all static spins and all moving spins are brought back to zero, to a phase of zero. After this, we acquire a scan with a bipolar gradient, and we get the moving spins that are proportional to the phase, and if we subtract this from each other, we have successfully removed the background phase. Now we have to do this, of course, in order to have a time-resolved acquisition with ECG synchronization. We do this by dividing the space between R waves into a certain amount of time frames. And within each time frame, that is also often called cardiac phase, we acquire now our reference and our flow-sensitive acquisition. We do this over time in order to slowly fill K-space to finally achieve our image that depicts the anatomy as shown here, as well as the pulsatile flow as can be seen here. Now we have acquired a 2D scene phase-contrast MRI acquisition with floating encoding in one direction. Here it is depicted in very bright colors and very dark colors or very bright white and dark gray value that indicates the direction of the flow. Now at this location where we acquired our 2D acquisition, we can now go in, contour the vessel wall and start quantifying numbers, for example stroke volume, net flow, reverse flow, regurgitation or peak velocity, to just name a few. However, the talk is called 4D flow MRI. So how do we get now from 2D to 4D? First, we have our one-directional flow encoding and a magnitude image acquired. We can, of course, extend this to three-directional encoding, which automatically extends scan time because we have double as many images. Instead of 2, we have now 4. We can further extend this to a volume, so we acquire a certain amount of slices that covers the anatomy that we are interested in. Doing this, we of course again increase scan time by the number of slices we acquire. As you can easily see, this dataset now gets a lot more complex. At first, we have acquired 2D in time in a single direction, then we extended to 3 directions, and then we also extended further to a 3D volume. So from just a few seconds, we now need 5 to 10 minutes to acquire the full data set. And of course, also data analysis gets more complex by doing so. So this is how it looks like. We acquire a 3D volume reference acquisition that is time resolved. We acquire a flow sensitive scan in one direction that is also 3D and time resolved. In addition, we acquire X and Y directions to achieve the 3-directional flow encoding. And if we acquire this dataset in the thorax or abdomen, we additionally need to take care of navigator gating to control for respiration. This is how a dataset typically looks like. It gets acquired within 5 to 15 minutes with a certain resolution. 4D flow stands now, and I would like to point this out. 4D stands for 3D volume over time, and flow stands for 3-directional velocity encoding. Now we actually have to go into our 4D flow MRI data to do some processing. At first, we perform usually a preprocessing in a certain order, which starts with corrections of phase offset errors as well as anti-aliasing. This is typically followed by a noise masking, the calculation of a 3D phase contrast angiogram, which often gets refined in a vessel structure segmentation. And then oftentimes also a center line approach comes into the game, where either planes are positioned manually or automated. Of course, then we can visualize using our angiogram as a mask, and we can extract quantitative parameters such as peak velocity, net flow, or pulse wave velocity, etc., to just name. I also would like to talk about error sources in phase contrast MRI. Here I want to talk about velocity aliasing. 4D flow MRI is acquired with a fixed velocity sensitivity, or bank. The bank is defined by the bipolar gradient that has a certain amplitude and duration. We have to set this bank above the expected maximum velocity in our dataset. If we don't do that, if the blood flows faster than the bank we have set, we get velocity aliasing. And this is how it looks like in the dataset. We have a vessel with a parabolic flow profile. If a couple of vectors are faster than the set bank, they get flipped over to the wrong direction and we get errors in flow quantification. In the image, this looks like that we have a sudden change from very dark areas to very bright areas. This can be corrected, but oftentimes if this is flipped over several times, it cannot anymore. We can also not just set our bank to an arbitrarily high value, because the bank also is proportional to noise. It can be seen here in this formula that noise, bank, and SNR are related. What one can do is you can go into the acquisition in an informed manner. So you could, for example, run a bank scout to find out what velocities you can expect, or you take information from a previously acquired ultrasound or echo. There are also concomitant gradient cross terms, also often called Maxwell terms, that are caused by switching the field gradients of spatial encoding and the velocity gradients. These are additional field components in X and Y directions that cause the resulting B field vector not to be perfectly aligned anymore with the Z direction. This error also increases with distance from the isocenter, as can be seen here. The error causes a phase accumulation and thus errors in measured velocity. This can be corrected in the image domain by just calculating the coefficients of a polynomial calculated from the applied waveforms, which was first shown by Bernstein et al. In MRM. Other error sources are, of course, eddy currents. A lot of people in this room know about these errors very well. Eddy currents occur due to switching of imaging and encoding gradients and cause changes in the magnetic flux, inducing eddy currents in conducting parts of the scanner system or in the patient. These are alterations of the desired gradient strength and duration. Here depicted in a static phantom, which should have the same gray value across this line, you can see that instead of this being a constant 0, we see instead a gradient, a spatially varying phase error in the MR images. Eddy currents get larger with stronger gradients, thus with a lower Wenck. The subtraction of phase images from the reference image, however, does not eliminate eddy current related errors, and we have to go in with additional post-processing, for example, by subtracting an estimation of the spatially varying eddy current field, as suggested by, for example, Walker et al. In this publication. Walker et al. Also describes in this publication how to estimate noise and how to reduce noise by using a certain approach that can be read in this paper. With 40 flow MRI, you also need to calculate a phase contrast angiogram, as I mentioned earlier. This is typically done by using the anatomy image, the velocities, and a combination of the velocities somehow. You combine the velocities with the anatomy in order to suppress the background, and then you get out an angiograms, such as this brain angiogram or aorta and pulmonary system, as shown here. This angiogram is now used to mask velocities within the vessels. Here we show path lines that depict the blood flow. Everything that is red flows fast. Everything that is blue flows slow. This is a brain acquisition that took about 15 minutes to acquire. Unfortunately, I don't have time to touch base on hemodynamic parameters, such as wall shear stress, pulse wave velocity, or pressure gradient. However, I would like to mention that there is an increased effort currently in automation and volumetric analysis workflows, for example, by using machine learning or by automating analysis pipelines using center lines. And with this, I would like to thank you for listening and also thank all my collaborators for their ongoing support.